just to review, basically, dynamic routing. It's not static routing, that's for sure. It's a whole new thing. Ooh, wait, I've even got my mouse work. Oh, man. It's like technology heaven for teachers over here. I'm excited. So we'll talk about the protocols and the different characteristics of the types we'll be working on. And then we'll dig in a little bit into how they figure out what the best way to do it and the difference between distance vector and link state and what the difference is, basically. So you probably remember a little bit of this from Cisco 2, particularly if you took the old Cisco 2. But we don't want to keep track of a bajillion static routes, right? So dynamic routing protocols take that problem off of our hands. And instead of having to figure out, you know, how do I get to this network? I have to go to this router, blah, blah, blah. They do all that for you. And they do that by agreeing on some kind of protocol, either an interior gateway protocol, something that happens on the inside. Man, I think my pen works too. Something that happens on the inside, or an exterior gateway protocol. If you remember Monty Python, Sir not appearing in this film, pretty much that stuff. We'll get to that later. The border gateway protocol, not appearing in this film. So they got to do all the stuff that a human would have to do to keep the networks up to date. They have to figure out how to get to the network they're going to. They have to figure out if the path that was originally the right path is no longer the right path. They have to figure out, are those networks still accessible? And they have to like keep that information up to date as time goes on. And then we will look at link state, distance vector, and then there's another path vector that we'll kind of gloss over a little bit. So distance vector routing, we send, like all of the routing protocols, we're going to send and receive messages on interfaces to the other routers that say, hey, I'm using this protocol, and I've got the following things going on. Those go back and forth. Again, if you're using the same routing protocol, the routers tell one another about the remote networks that they know about. So eventually, router 1 here figures out what's going on with router 3 and learns how to get clients to networks in that 10.4 network. Something changes, routing protocols say, hey, we just lost router 2 and there's router 4 up here that can get us to where we need to go. We can change the path we use to get to it and move on. So convergence, hopefully just to refresh your memory, is once the network's kind of got all of its stuff figured out, right? The network knows everything about the network. All of the routers are hip to all of the other routers' routing tables, and we know how to get from FA0 on router 1 all the way to FA0 on router 3. And the way that works is we start with the routers directly connected to us, what networks are here, and then what's the network that's 1 hop away from me? All right, what networks do you know about 1 hop away from you? And the way you judge a routing protocol is kind of based on like how fast that process happens and how well it happens. So you can use just the number of hops. If you remember RIP, that's how it figures things out. It's 3 hops away. That's got to be the furthest away. Even if those 3 hops are cell phone links and there is a 4-hop Ethernet connection that you could make, RIP's still going to say, well, let's do the cell phone links anyway because there's fewer hops to screw up. So you can start bundling into that the enhancements in there that go along with it. You might want to know not only about the hops, not only about what you're connected to, but what else is going on those links. How good are they? How much do we trust them? Then you need to come up with some kind of algorithm to work with. Some way to figure out, based on these numbers, what does that equate to? And then you send that information around when you're sending around your routing tables. You say, hey, not only is this way a hop away, but it's also a slow hop away. So take that into consideration when you're making up your mind. And then, like with all dynamic routing protocols, when something happens, it takes that into account and change it. So when we got to RIP v2 and EIGRP, we moved some stuff in there. So notice RIP1 misses a lot of things. It sends all of the updates out to the broadcast address. It doesn't know much about variable length subnet masks. So that thing when we got rid of the classful networking, classless interdomain routing, or CIDR, doesn't know anything about that. It doesn't know how to summarize up a route, and it doesn't know how to handle any kind of authentication. One of the problems you can get into with a routing protocol that doesn't know how to authenticate is that an adversary can create a person in the middle situation where the router sends the not real router, the adversary sends a router update that says, hey, send all your packets to me first, and RIP will just let you get away with that. So more modern routing protocols build that stuff in. They support variable length subnet masks. They support classless interdomain routing. They summarize their routes, which just means that, say, all the stuff for 192.168 is on the other side of that, even though there's multiple networks over there. In order to save space in our routing table, we just summarize all that stuff up and say, you know what, if you want 192.168 / what is that, 16, all that stuff's over there. Go out serial interface 0 or gigabit interface 1 or whatever it is. So those are the kind of things that kind of grew in there. So link state dynamic protocols sit there and figure out the shortest path first. Let's back up to this one. Routers first figure out where the things are connected to, same way as before. So like who's plugged into me, and then who's plugged into who's plugged into me. They use hello packets to do that. You build that that data starting with who you're directly connected to. You use link state packets that you flood to your neighbors, and then they flood onto their neighbors. Then you create a database that includes the whole shebang. It figures out this whole network topology here based on the cost of it, not just the number of hops to it. Each router works that out for itself. They build their own little shortest path first tree. Ideally, when all of that gets worked out, as long as nothing's changing, convergence happens when we've all got the same SPF tree figured out. So every router in our drawing here knows about every other router, and we all agree that this is the best place to get to the best, to whatever network from whatever point. They should all agree. And then they throw all of that into the routing table. So the upside, you wind up with that complete map. Convergence happens faster. The topology changes and an update changes. We're not constantly sending updates. So we're saving on the amount of communication that happens on the network about the network. There's going to be some overhead on any network with like the network describing itself to itself, but these keep it down since they only tell you when something changes. And then they include concepts like areas and summarization. We'll look at areas as we get deeper into OSPF and setting one area or multiple area and then summarizing the networks that are in there. It is a little heavier to do this, right? Because we created an entire database that lives there instead of just a list of routes. The brain of the router is going to work a little bit harder, and if you compare it to the processor in a computer, router processor is a little on the weak side. So takes up more CPU, takes up more memory to calculate all that mess and put it into its brain. And then during the process of convergence, all of that link state flooding that goes on, that chews up a lot more bandwidth. So although you get to convergence faster, the process is more bandwidth intensive, but generally superior. So again, just to summarize briefly in a really well put together slide, dynamic routing protocols take us out of the equation for figuring out how to route packets around, important. They burn CPU and memory to do it, but that's why we pay them to be computers. Sometimes generally people will use a combination of the two protocols. Generally on stub networks, on networks that don't connect to networks, they are just the end of a network. Generally you'll use a static route on those so you don't have to play the whole dynamic routing game and you save on network traffic. Once all those things merge, we call that convergence, and we grade routing protocols based on their ability to do that quickly. You can either figure out the best path to get somewhere, like even though there's 3 hops on our cell phone link and 4 hops on our Ethernet link, one is shorter, there's fewer hops. It is not the best path because the cell phones are slower. Or you can do they are the best path, not necessarily the shortest path. Distance vector doesn't know about the maps. The modern version of that is RIP-v2 and RIP next generation. And you might see RIP-ng installed places. RIP-v2 doesn't know about IPv6 yet. If you've got a link state protocol, they create the complete shenanigans. They figure out the entire layout of the network. I'm going to put complete shenanigans on my gravestone. And then if you want to do a deeper dive, look up Dijkstra's algorithm and figure out how they calculate the bestest route. That's the algorithm they use for the shortest path first. It accumulates those costs along the way to come up with the whole cost. And we will talk very briefly about is, but more about open shortest path first. And that's like the high level view of dynamic routing.